Here I am in the beautiful city of Medellin metropolis, known as the most innovative city in the world, and also as the only epicenter of technology for the fourth industrial revolution in the Americas, including the USA. The beautiful city of Medellin, with its gorgeous and absolutely stunning green avatar mountains of South America, served as the inspiration for this workload and this video of my development of the prototype for the blood pressure monitoring system. So the ambulatory blood pressure monitor is designed as a wristband type for higher portability and convenient wearing, such as I have illustrated in this workload and I have shown in this video. The ring-shaped band can be worn on the user's wrist with an air pocket inside the annular band that applies pressure. The ambulatory blood pressure of the user is measured by a pressure sensor that detects the air pressure inside the air pocket and measures the blood pressure waveform. The detailed components of the proposed ambulatory blood pressure device and architecture is also illustrated and shown in the video later on, and also an explanation of all the software algorithms and all the software models are given. The measurement of the blood pressure can be represented in 5-step process. First, the blood pressure gauge is set near the user while keeping the band air pocket, such as the first part that I have explained earlier in this presentation, in contact with the user's wrist. Next, the air pressure is moved from the second part air pocket to the first part air pocket to increase the internal pressure on the first part air pocket, which is attached on the user's wrist to enable the biosignal waveforms are analyzed to derive an optimal value of the internal pressure of the first part air pocket. After that, the internal pressure on the first part air pocket is set to optimum value. Finally, the blood pressure of the user is measured as a continuous waveform. Increased blood pressure in the arteries is a common condition that leads to heart diseases and cardiovascular diseases. So, an accurate measurement of BP, blood pressure, is vital for the prevention and treatment of all of these heart diseases, especially in hyperintensive patients. The proposed system is based on the oscillometric pressure waveforms methodology, and it is combined with Bluetooth module and technology in order to transfer data to any mobile application. The system architecture consists of the blood pressure architecture consists of a hardware system implementation based on a CISC reduced instruction set computing system. The hardware of the tool is made up of the main CPU board that serves as a controller, and it works from a blood pressure device. The sensor displays systolic an air pump and solenoid as the pump and air regulator that will enter the handcuff, and SD card module of the main CPU storage system that will store measurements, data measurements. The main neuromorphic RISC architecture will give an order on air pump that will pump air slowly into the cuff, the wrist cuff, while the sensor that detects the air pressure inside the cuff will continuously monitor the pressure until the desired pressure is reached, about 170 mmHg. When the required pressure is reached, the blood flow will stop for a while because the cuff presses strongly on the blood vessels. Next, the valve will automatically open and the pressure on the cuff will slowly drop. As the pressure drops, the cuff strength presses on the blood vessels as well. When the pulse occurs for the first time, the pressure on the cuff will change slightly and the pressure changes will be detected by the sensor, which will then be processed by the main neuromorphic RISC architecture as systolic pressure. As the air pressure drops on the cuff, the pulse detected by the sensor will gradually disappear, and that is when the diastolic pressure values are obtained. A pressure sensor driving circuit was developed to implement the wrist vein tonometric method using a tonometric pressure measurement module. The main CPU, the neuromorphic architecture model, was used as the main driver module for sensor data processing and wirelessly communication control. The main CPU uses an Atmega 328 as the main processor and will support 8 analog inputs and output ports and 22 digital input and output ports. The pressure sensor driving circuit takes an ADC resolution and motor driving module for close contact between pressure sensor and blood vessels. With the cuff positioned at the radial artery of the user's wrist, the band air pocket was inflated to expand the cuff, compressing the radial artery and measuring the pressure change on the cuff through the beating of the radial artery. I designed an automatic feedback algorithm for motor control, so an error in the analysis increases as the cuff pressure changes due to patient's movements. Thus, an algorithm for estimating the optimal cuff pressure is developed to automatically control the driver motor so that the cuff pressure remains constant. The measured data by the pressure sensors are divided into pulse waves and cuff pressure using a digital filter, and the optimum cuff pressure is estimated by calculating signal-to-noise ratio of the pulse waves according to the cuff pressure. The driver motor rotates to inject more air pressure when the measured cuff pressure is lower than the estimated value. Otherwise, it rotates in reverse to release cuff pressure, as it is shown by the software models and the software scripts presented in this video. The artificial intelligence machine learning models were used for data type was applied in order to analyze the ambulatory blood pressure data pattern of the user. So the normal and abnormal blood pressure classification based on TOAST was defined through logistic regression analysis, and only the preliminary work for the accuracy analysis of the existing 5 levels LAA, SVO, CE, UD, OD was determined. So the ambulatory blood pressure data analysis model was applied, and the blood pressure information collected through the ambulatory blood pressure measurement device to determine the abnormality on the user's blood pressure. So first, the low pass and shock filters were used to pre-treat the ambulatory blood pressure and extract the features, followed by pattern analysis performed through logistic regression analysis based on the classification of the initial clinician of the training data. In this section of the blood pressure system, the blood pressure digital artificial intelligence system, I will explain not only the software methodology, but also the different software tools, which are based on an IDE software development tool, including the software algorithms and models and scripts based on Python and also based on C++, high-level language. The software for the blood pressure, the software methodology includes the wire.h file, which is the I2C library for the CPU board. It includes also the bus interface. So define the macros. It contains the start button of the blood pressure unit, the BP unit. Also, it will define and set pins for the start pin and the begin measure pin of the blood pressure unit. These are different functions which form part also of the software methodology. Then within the script, check if the measurement is completed. The CPU will get the data from the monitor display unit. That is part of the software environment. Now let's set the software global variables contained within the software script and the algorithms as well. Here, you can indicate the available data from the I2C bus. It will also tell you the total number of data collected as it is shown on line 8 through line 10 of the software script illustrated in the video. Then it will store the measure value of the systolic, diastolic, and the heart rate. Now let's proceed with the void setup within the main program as shown on lines 10 through 19. Now let's set up the serial to begin at 115200. So start at the output. Value open initializes the data, the address of the EEPROM, which it is 0hex50. Now initialize the interrupts for the I2C data. Then, at the void loop of the software script, set interrupt service routine, so you can actually read the data as it relates to systolic, diastolic measurement readings of the BP blood pressure unit. See lines 68 through 90 of the software model presented in this video. So the CPU is instructed via line 24 of the script of the main software model software program for the BP, which is the blood pressure unit, to start getting the data and or start the measurement. Now via line 26 of the voice setup within the main script, emulating the data of the blood pressure unit. As you can see in lines 26 to 28 of the voice setup. Now lines 30 to 36 set a delay of 2 seconds and secure the value is closed, and then collect and transfer the data of the measured by the blood pressure unit. And then line 52 through 61 of the software module will print the desired and the data and the measurements from the blood pressure unit. And that's basically the software methodology. It's not extremely difficult.